DNS servers also cache data. And this is not the first time we hear this term caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects so we could reduce delay, we could save some network bandwidth. You see here, DNS for the same purpose also caches IP name mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. So let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay? Again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out, but the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force. Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay, well, to be more precise, the resource records. Okay, and each look like this: a tuple of 4 elements. This is usually the host name, and this is the IP address, and this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. Right. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says hostname at the name and IP address at the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here, the C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize, but the actual name for that machine should be this, server is backup2.ibm.com. Right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry, right? So the name there is a domain, okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers. Next, the DNS protocols messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are two parts though. From here and up, this is the message header. From here and down, the data part, where the actual mapping, actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next thing, the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS servers saying, no, that's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. Right? There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part. Because the number of questions a DNS message can carry is variable. Now, in order for the receiver to know how many lines, how many records it reads, it looks up here to find out and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the answer entries, however, then you see the full RR, the full resource records. Okay. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used. Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so 2 things you need to do. First, register your domain name with the DNS registrar. Now, being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the network solution there, will try to insert 2 records. Okay. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now, back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website. Attacking DNS. This is the last bit of DNS. So we're going to talk about attacks in 3 parts. First is attacks targeting the hierarchy of the DNS. Second is to target more the client who need DNS service. Third, then is to exploit the DNS service to try to pull off attack for some other targets. So let's go back to attacking the hierarchy. So a hacker could actually hack down a number of machines around the internet and have these machines bombard the root servers with lots of DNS queries. Right, so having very few root servers around, this can potentially be dangerous and bring down the DNS service entirely. But nowadays, now it's hard to pull off, mostly because the local DNS servers will cache the TLD servers. This allows all the local servers to bypass the root server entirely. Right? So there's not much traffic going to the root. If the zombie machine sends a lot of queries, chances high that they'll only go to TLD instead of the root. Right? Not to mention that one could set up firewalls, okay, nearby the root servers. So those very few root servers are well protected in a way. Now, attacking the TLD servers then is more feasible, all right? Because queries then all go to the TLD these days. Good, so it's more dangerous. But the thing with the TLD server is that the number of these is way higher than the number of root servers. So the hierarchy there is pretty robust, to be frank. The second type is the redirect attacks, but I would rather call that this is attacking the user of the DNS service. First is the man-in-the-middle attack. What the hacker does here is just to intercept the queries. Therefore, it's not going to reach anyone in the hierarchy and therefore no answers back to the users. Second one, on the other hand, I think is meaner, DNS poisoning. So the hacker there is actually sending false replies. So when local DNS server caches these replies, the users will be thinking, "Oh, I thought I'm going to the www.google.com, but it's actually going to a hacker's website." Not very good. So nowadays, network admin for the local DNS servers needs to be careful and check the sources of these replies. Last one, exploiting DNS for DDoS. We actually hear about this already. So this is in chapter 1, I believe. Okay. So people are sending queries. Hackers can spoof these queries and replace the source address, okay, with the IP address of the attack target. As a result, the servers in the hierarchy will be all sending replies to this guy here, okay, and therefore denying this machine here to go out and reach the rest of the internet. But this is also a bit hard to do because you have to hijack enough of these queries. You need to spoof enough of these queries, right? So you need amplification in order to make sure that the service is really denied, okay, at the target IP. And that's all for DNS.